Any of our TS? Okay, thank you. So we continue our discussion. We have discussed in details the state space representation, where we define things by a state or a configuration, a set of state transformation rules, validity checking at states, goal state, start state, and given this, we consider today searching OR graphs. So we will pick up the topic of searching OR graphs.
Hello.
Yes.
Sir, please accept the request in the team.
Yeah, that will be done.
Okay, sir.
So here, because all nodes are OR nodes in the state space definition, so given a start state, a goal state, a state definition and state transformation rules, the objective is to find a path. The objective to find a path. And while we find a path, we would also like to use what are called heuristics. But before we proceed to start searching using heuristics, we will first do the basic algorithms and then move over to the more advanced algorithms in a step-by-step manner so that we are able to understand the whole process in a better way. So there is a framework by which the algorithms work, which means that you are systematically exploring the implicit graph and making it explicit. So initially we will develop and study 3 such exploration algorithms which are well known, but the framework will be provided so that we understand them carefully, and then we will be able to see what the nuances are as we move ahead. So the first algorithm is called depth first search. In depth first search, in AI parlance, in this sort of definition, we use 2 basic data structures. One is called the open list. The other is called the closed list. The open list typically contains frontier nodes of the search. Nodes here mean states. Contain frontier nodes of or states which have not yet been explored or expanded. That means their children have not been created and we have not seen further down the nodes in the open list. So they are called open list. The closed list is set of nodes or states whose successors have been generated and made explicit. So initially, in step 1, initially the open list consists of the start state S. So that is the initialization step. The next step is the select step. So we would like to select some node from the open list. In depth first search, we select the first node from the open list. If open is empty, that means there is nothing else to explore. We terminate. Now, having taken out a node from the open list, having taken out a node n from the open list, in step 3, we examine whether this node is a goal node or not. If it is a goal node and our objective, if it is a goal node and our objective is to be able to just find any solution to the goal, then we can terminate. On the other hand, if we want to find the shortest length solution, the shortest cost solution, then depth first search does not guarantee the shortest length or shortest cost solution as we can imagine. Now, if it is not a goal node, so if it is a goal node, then there is a termination or continuation decision. If it is not a goal node, then obviously, or you have decided to continue, then what you do is you start generating the children of the node n. That means you had a node n and you generate the successors n1, n2, and so on and so forth. Nk. Can anybody tell me how do we generate the successors?
Based on the state transformation rules.
Correct, based on the state transformation rules. And then after we have removed this node from open and we have generated the children, we put n in closed. So n is put in closed because the closed list is those elements who have already been examined and children have been generated. Now we start examining the children. Once we examine the children, then these children could either already be in open or closed, or they could be new. If they are new, then we put it back to open list. In depth first search, we put it in the front of the list. And in breadth first search, where would we have put it in?
End of the open
At
list.
the end of the list.
Right. In breadth first search, we would put it at the end of the list. Correct. Now, if a node is already in open or closed, then you can take two decisions. One is, if your objective is to find any path, then obviously there is nothing to do. You don't need to regenerate this node. It is already there in open. Or if it is in closed, then it has already been explored. You have just come by another path. If a node is already in open or closed, then you have come by another path. Because you have come by another path, therefore, you now have a choice of what to do. On the other hand, if you are interested in the shortest length path or the shortest cost path, then you would need to examine the new cost or the new length that has come. And accordingly, you will have to take a decision. And after you have done all these things, you have revised open, updated, closed, you go back to step 1 and again step 2 and again pick up some node in open. So this whole process is the search process, and which node you take out from open, how you put the nodes back into closed, how you look at nodes which are already in open or closed. All these bring about different variations of the algorithm. So let us now look at an example. Let us look at an example. So we know, let us look at an example of depth first search. So in depth first search, what do we have? Suppose this is our implicit graph. We are given 3 goal nodes, and we are given the start node, and we are given state transformation rules. For the sake of our understanding, I have created this graph, small graph, so that we understand what to do. So now tell me, in the beginning, in step 1, open consists of the start node and closed is empty. So which node will be taken out from open now in the algorithm? What is the next step in the algorithm?
Select A.
Select. So A will be selected. A will be selected. Is A a goal? Then the third step is goal testing. So our steps are what? Initialize. Let us write down our steps. Select. Can anybody tell me what is the third step?
Checking for goal.
Goal testing. What is the fourth step? Expansion. And what is the fifth step?
Continue.
Go to 2. So these are our steps. So let us remember these steps. So if we do depth first search, then in the second step, what will be the children generated? B, C, D. And what will be put in closed? A. Now which order I put B, C, D? We have to decide on an order. We can put left to right, we can put right to left, some order we have to put. But we will put them in that order in that list, and the search will depend on the order in which you put the nodes in the list. Is that clear? So let us say we have put B, C, and D. So now which node will be taken out next? In step 2?
B.
B, node B, because in depth first search, we are starting from the beginning of the list. Now when node B is taken out, then B is put in closed because B is not the goal node. And which nodes are generated?
E, F, and G.
E, F, and G are generated. Now since E, F, and G are generated, and they are put in the front of the list. They are put in the front of the list in DFS search. In some order. The children are ordered in some way and they are put in front of the list. Therefore, open list is what kind of a data structure?
Stack.
Stack.
Open list is a stack. Now, which node will we take out?
E.
E.
E will be taken out. After E is taken out, which are the children which will be generated?
I, J.
I and
J.
J. Now, once I and J are generated, then next which will be taken out?
I.
I will be taken out, and I is the goal node. Because I is the goal node, I have two choices. If my objective was to find the goal node, any path to the goal, I can terminate. But if my objective is to find the shortest length path to goal, can I terminate?
No, sir.
We have to explore more.
Then what would I have to do?
Put I in the closed list and go back to E.
No, there are few more things I have to do because I have not maintained the length of the current path to the particular node. Nah? Otherwise, when I come to a node again, I need to know whether I have come by another path. Isn't it?
Yes, sir, like few more parameters need to be stored.
So yeah, either I check open and closed. If I don't check open and closed or whatever I do, I need to maintain for every node and another variable. So let us call that variable Gn. Gn is the length of the path of the current path to n. So Gn is the length of the current path to n. Let me rewrite it a little neatly. So I maintain a Gn value. So when I start, what would be the G of the start node?
0.
0.
What would be G of B, C and D? So this would be 0. What would be G of B, C and D when I generate here? In
1.
1.
1. What would be the G of E, F and G when I generate them?
2.
What would be the G of I and J?
3.
Correct. And anything else I have to do? I also have to maintain something called current best. Because the first solution need not be the goal node. So I have to maintain something called current best if I want to find the shortest length path to goal. And I will initialize it to
the first path we have ever found.
Initialize in the beginning of the search, I will initialize it to infinity. And whenever we find a path, so now whenever I have found a goal node, what will I check? If
it is less than CB.
Correct. If Gn is less than CB, then
Gn equal to CB.
CB equal to
Gn.
Correct. Then CB will become equal to Gn. Very good. So you all are getting the hang now. So now in this algorithm, few more things I have to do. If I find a node which I have generated in this expansion step, whose GNI is greater than equal to CB, then what do I do? Even if it does not exist in open or closed, what should I do?
Put it in closed.
Discard.
Yeah.
We got to
Yeah.
So this step is known as pruning. So I will ask you to modify that depth first search algorithm on your own and now make sure that now you can come to a node again. So you work it out on your own and I would like to see what happens. So after I have found I, after I have removed I from here, what will happen to J? After I have found a node, when I remove J, do I do anything with J?
We discard J.
We discard J. Very good. Then I will remove F. And F will be having a G value of 2. What are the children of F?
G and E.
G.
E, I, G.
E, I and
H
G.
and G.
Now E is already enclosed. Its current G value enclosed is 2. You are going to come to it with a new G value of 3. So you do nothing. Correct? To this E you do nothing. Now to G also you do nothing, and to I also you do nothing. So the action on F is nothing to be done. Next, which one will you remove from the list?
G.
G. And what are the children of G?
H and J.
H and J.
H and J. For J again you'll do nothing. But for H what will you do? What will become its G value?
3.
3.
2.
3.
Discard.
And you will discard. Got it? So you will discard this G, this H. Now what will you remove?
D.
D.
C.
C. You will remove C.
C. From H to C.
Because you have removed here you have removed B. C and D are still there. So now after you remove C, what will be generated?
D.
F, G.
F and G.
F and G. And what will you do to F and G? Nothing to be done.
Nothing.
Yeah, nothing.
Because you're coming with the same value of G, the cost small g. Next, what will you remove? D. What children will you generate?
G and H.
G and H.
What will you do with G?
Nothing.
What will you do with H? Because H has been discarded, you remember? So
G
now
value.
GN is 2.
New CB will be, new GN will be 2. So
the new GN will be 2. And once the new GN is 2, which is the only node left in the open list?
H.
C.
H. H. Now you will remove H. It is a goal node. You will compare with CB
CB.
and update CB to 2.
2.
CB was 3. Now CB will become. And now open is empty. So you will terminate. Have you got the hang of it now? Is that?
Yes.
Yes.
Yes, sir.
Good, good.
Yes, sir. Yes, sir.
Very good. Now let us go and do depth first, breadth first search. In breadth first search, again, our steps are initialize, what is the next step?
Select.
Select. Third step,
Goal test.
Goal.
goal test. Fourth step,
Expand.
expand. And fifth step, continue.
Continue.
Very good, very good, very good. So in breadth first search, you will again start with the same situation of open list A and closed list empty. Then B, C, D will be put. A will go to closed. Then which will be removed? B will be removed. Correct? B will be removed. And E, F, G will now be put at the
End.
End of the list.
So this data now open is behaving like what data structure?
Q.
Q.
Very good. Now open is behaving like a data structure Q. So now next, which will be opened? D. Taken out is D. And what will be put when D is taken out? Sorry, C is taken out. When C is taken out and put in closed, then what will be put in open? F and G
F
will
and
be
G.
put at the E, F. Right? We have taken out B and put, we have taken out B and then the children of B, E, F, G are put at the end and D is remaining in front. So now which node is taken out?
D.
D.
Now D is taken out and what is put at the end?
H.
H. Now what is taken out? E is taken out. And I and J are put at the end. Then F is taken out. And because I is already there, G is already there, you do nothing. Then what is taken out after F is taken out?
G.
G.
G is taken out. Again, its children J is there and what is now put? H is also there because H came from D. Then H is taken out. And when H is taken out, then H is a goal node. Now because H is a goal node, again you can stop if you want to find the first solution. But if you want to find more than one solution, then what will you have to do?
Continue.
You have to continue like we did in DFS. So you are suggesting that we start with the current best equal to infinity. And when we found the first solution here, now the current best is 2. Now, can you tell me whether DFS has a BFS or this breadth first search has any special property?
It is going level by level.
It is going level by level. That means first it is looking at all nodes whose GN is equal to 0. Then it will see all nodes whose GN is 1. Then it will see all nodes whose GN is 2. You know, this is the sequence in which it does, isn't it? So the first solution that it gets must be
Minimum length.
Shortest length. Minimum length.
Yes. BFS first solution is of shortest length. Very good. And also, if you have come to a node which already exists in open or closed, then what is the meaning of it?
It's in a level we have already covered.
It's in a level we have already covered. That means now you are coming to it with a longer path. Got it? So all the things that you did in depth first search to ensure that you are trying to find the shortest length path, you don't need to do in breadth first search. Anybody has a doubt up to this point?
Hello?
Yes.
Sir, in case of BFS, we will get the shortest cost path, but we cannot know what path to follow, no, sir?
No. Whenever you have generated the children, you maintain a parent pointer to the node from which you generated the children.
So in this case, we got H to be the closest one, but do we store the path that we have to go from A to D and then D
so
to
how
H?
do you store the path? Can anybody suggest how you store? All you need to store, whenever you generate children, you need to store the current best parent. So for every node, you will maintain who are its parents. In breadth first search, you will just maintain parents like this. And whenever you reach a goal node, you just move along the parent path, parent pointer path. You will find the path. Have I answered your question?
Yes, sir. I am saying in case of depth first search, in
case of depth first search, as soon as you come to a node again with a smaller length path, you change the parent pointer.
So once we reach H, then we have to go back again to A, sir.
Just a sequence. If the path length is L, then L point steps you have to. Anyway, you have to find the path. So you maintain the best path. There's nothing wrong there.
I'm saying, in case of parent pointer for H, how will we store only D and not G?
As I said, whenever you generate a node in this expand step, okay, let's go to this. Whenever you have generated the node, whenever you have generated the children, generate the successors, then you mark the parent pointer.
Okay, sir.
As soon as you generate the children, you mark the parent pointer. In DFS, you will have to update the parent pointer whenever you come with a new path, if it is already in open or closed. But in BFS, as we have seen, you don't have to do it.
In DFS, if we directly follow the path as it is in the closed list, we will get the path.
No, closed list can contain many nodes, no?
Okay.
See this
it will
example.
only work for first one, yes.
Closed list can contain many nodes. Closed list will contain all nodes that you have seen.
Yes, sir, yes.
So parent pointer is essential. So my question is BFS much better than DFS then? Because BFS first solution is goal. It does not look at any nodes whose cost is more. Then what is What is the flip side of BFS?
It takes more.
It takes a lot of memory.
All the
Yes. So let us analyze what is the memory requirement a little better. So if I just draw a structure like this, if I just draw a tree, forget about a graph. I'm drawing a simple tree. A simple binary tree. And let us assume the goal is somewhere here. Then DFS, its memory requirement will be how much? Will be proportional to, if L is the depth of the tree, then DFS memory requirement will be proportional to L. Because it will generate in one direction and then again it will backtrack and go in another, and BFS will be order of
number of nodes in the tree.
Yeah, in this binary tree it will be exponential. So in the worst case, BFS can be exponential and DFS, but the problem with DFS is if one side of the tree is infinite, then you end up in trouble. What is your trouble? Your algorithm will go on in an infinite direction. In a hypothetical such search tree, one direction not only infinite, it can be very large. It can go deep down. and you can either find the solution or not find the solution. So suppose this is the tree, the solution is here, DFS will go up to here. So if the solution is here, BFS will stop here. Sorry, it's not coming in the screen. No? Yeah, and DFS will go right here. So DFS will go right to the base, whereas BFS may stop wherever the first goal is. So these are the flip sides, and for very large state spaces, BFS's memory problem is a serious problem. So what is the solution? Anybody who has seen the video can tell me the solution?
Iterative deepening.
Yes. So the solution is iterative deepening search, which is called IDS or iterative deepening depth first search. Iterative deepening depth first search. So what does it do? Can anybody tell me what it does?
It does depth
Checks the
first,
just
level by
next
level.
level.
Yeah, so this does depth first search level by level. So what is the high level algorithm? So it does if so initially there is a depth bound. This depth bound is initially set to 1. So let dB be the depth bound. Let dB be the depth bound and let the depth bound be initially set to 1. So it calls DFS with depth bound. It calls DFS with depth bound. And the result may be a solution is found. A solution is no solution found. Two options are there. If a solution is found, what do we do?
Terminate.
Terminate. If a solution is found, we terminate. And what is the guarantee? That this will be the
Minimum length.
minimum length solution. If a solution is not found, what do we do?
Increase the depth bound and run again.
Restart DFS DB. So, sorry. So we set DB equal to DB plus 1 and again do DFS DB. So by this, we have guaranteed that the first solution is minimal and the memory requirement is the same as depth first search. Correct? Isn't it?
Yes, sir.
The memory requirement is same as depth first search.
Slightly more.
No, you're doing it, you're repeating, you're flushing everything off and starting again.
Okay, yeah.
And you don't have this pitfall is not there. This pitfall diagram which I had drawn where the solution may be higher and DFS can go in one direction as deep as possible, that pitfall also does not exist. But what is the flip side?
It takes more time.
No, let us, that more time comes from where?
Because you're calling depth first again from the start point.
Yeah,
Again.
so it re-expands nodes.
Yeah.
So it re-expands nodes. Now, is everybody okay with me? Do we want to see how iterative deepening works on our example? Or is it clear?
Sir, it will be better with an example.
Yes, sir.
Yeah, let's go and do that example. Let it come. I think it is going to come. So this is not what has come on the screen. Just wait. There is some time lag for the. Has the slide example : searching a state space graph come?
Yes, sir.
Yes.
So let us look. It is good. It will start with DFS 1. And when it starts with DFS 1, in this iteration, which nodes will it see? A, B, C, D. Correct? It will see A, B, C, D.
Yes, sir.
And after seeing A, B, C, D, will it find a solution?
No, sir.
So what will it do? What will it do?
DFS2.
Yes.
It will DFS to.
It will do DFS2. Now it will see in what sequence? It will see A, B, E, F, G, C. Sorry, A, B, E, F, G, C, D, H. Right? This is the sequence. DFS2 will go in what sequence? A, then B, C, sorry, A, B, the nodes expansions. I'm talking about the nodes that are generated, expanded. So our first A will be done, then B will be expanded. Then what will be expanded after B in DFS2? E.
Yeah.
Then E,
F and
then F, then G, then
C.
C,
D.
then D, then
H.
and you will terminate. Got it? Have you got it? A, B, E, F, G, C, D, H. That is how it will happen and you will terminate. If you did not find a solution here, suppose H was not the goal. Suppose H was a non-goal node. Then what would you do?
DFS3.
Then you would have to do DFS3. And in DFS3, what would be the sequence?
A, B, E, I.
Stop.
Yeah, I
A,
stop.
B, E, I stop. Got it? Suppose H is not the goal node, then you would have to do DFS3 and the sequence would be A, B, E, I, and this being a goal node, you would have stopped. Is it now clear to everybody?
Yes.
Good. Anybody else has a doubt?
Yes, sir. Sir, how will we check that we have visited one node previously? Means it is a stacked kind of thing. So
yeah, so there are two options. One is you can maintain. So then this is a very good question. If it is a stack, then in a stack you don't maintain that data structure. So if you want to maintain a pure stack, then either you have to search linearly in the stack or you have to maintain a better data structure. And we'll come to those better data structures very soon. Good question, very good question. Remember this question, because typically DFS, if you maintain only a stack or you write it recursively, then you don't remember anything, you regenerate nodes. And that leads to newer pitfalls. Because if it is a graph and you don't check, then can you imagine what will happen if it is a graph and you don't check? Then you will go on repeating, and for a simple problem, you will generate exponential number of nodes. Have you understood what I said? Who asked this question?
Sir, Chirag.
Chirag, see, if I agree with you, but suppose it is a graph and and this graph is like this, and you can make this as large as you want, and so on and so forth. Then if you don't check and you go on doing, then you will end up in some trouble, because even though there are n nodes in the graph, you will start exploring exponential number, and you can draw this sort of a chain structure for a large number of times, and you will go on exploring the same thing twice, and you can show that there will be exponential complexity. Work it out. Think about this. These are very, yes.
We are maintaining a closed list, right? So
we are maintaining. What he said is that if you don't maintain.
Okay.
So now once we have understood iterative deepening, let us go back to our analysis. Our analysis is how many nodes are re-expanded. How many nodes are re-expanded? So if it is a binary tree and the goal is at depth L, we know that DFS will expand proportional to L nodes and PFS will expand proportional to 2 to the power L nodes. But let us now look at how many nodes will be regenerated by iterative deepening algorithm. So that is a very important thing for us to remember. So in this screen, thank you screen, there, if we have drawn this binary tree on the left, then in the first iteration, how many nodes are expanded in iterative deepening? 1. Correct? In the first iteration, how many nodes are expanded?
2, right, sir?
No, expanded. Generated are 2 more, but only the first node is expanded.
Yes.
And how many nodes are generated? 1 plus 2. In the second iteration, so this is iteration 1. In the second iteration, how many nodes are generated? Expanded? 1 plus 2. And how many nodes are generated?
7.
1 plus 2 square. Correct? 7, how does 7 come? 1 plus 2 square?
Yes, sir.
So we now have a formula for how many nodes will be generated in the ith iteration. So in the ith iteration, 1 plus 2 plus 2 squared plus up to how much?
2 की power I.
-1 -1.
So 1 plus etc. etc. So it will be like this, isn't it? So many nodes will be expanded, and for generating another 2 to the power I plus 2 to the power I. So for iterative deepening, you have to just add the total number of expansions in every. So now you have to find this new series is 1 plus 1 plus 2 plus 1 plus 2 plus 2 squared plus and so on and so forth. This new series you have to find summing up all the nodes that are, and I leave it to you as an exercise to see what happens in this case. How does it compare? Because it has to go up to level L. How does it compare with breadth first search? So this is another small exercise that all of you can do.
For the ith level, it is coming 2 to the power I only, no? 1 plus 2 plus 2 square plus up to 2 to the power I, right?
In the second iteration, if this is the number of nodes, so then in the second iteration, how many are the number of nodes expanded?
Okay, yeah.
The number of nodes
Yes,
generated and expanded are varying by 1 extra 2 to the power.
Yes, sir.
So you can find out that IDS in this special case of a tree will be order of 2 to the power L plus because what is 1 plus 2? It is 2 squared minus 1. What is 1 plus 2 plus 2 squared? 2 cubed minus 1. So all this will add up and you will just get one extra term power, isn't it? Do the calculation. If you have forgotten a JE calculation, then I don't want to do geometric series calculation. So in good cases, iterative deepening expands about double the number of nodes of breadth first search. But because it takes less memory, it can work on small computers. And then you can use your cache memory and you can use a lot of memory management techniques to make it very fast. Therefore, in problems like the puzzles and all that, iterative deepening is a much faster algorithm in actual execution than breadth first search. So we'll end here with a note for you to remember that now, instead of finding the shortest length path, if we assume that every state transition has a cost, that means if I generate N1 from N, then there is a cost. If I generate N2 from N, there is a cost, etc., 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 like in the traveling salesperson problem. So now my objective would be, how do I modify depth first search, breadth first search, and iterative deepening search to handle costs? And once I am able to handle costs, how do I incorporate what are called heuristics, or what are the problems dependent, problem specific information? That we will do in the next class. Any questions? Those who have another class can leave. I don't think there is class now, no? So any other questions?
Yes, sir.
Yes.
Sir, in the implicit state space, is there any chance that the node with the shortest path is not being considered?
In breadth first search, it will never happen. Because you're using the search space, you work it out, you try to find an example where it will not be considered. It will not come.
No, sir, I'm asking in, like, we are considering A, B, C, D from the explicit search space, right? We are not considering the whole explicit
No,
search space.
but you are generating the explicit search space systematically by the state transformation rules.
Yes.
So if you apply the state transformation rules, you are going to open up the implicit search space systematically, and by opening up the implicit search space systematically, you will not leave anything out. If it exists, then you have not expanded and generated all the successors.
Okay.
You can stop the recording. I don't know, Plavan, did you start the recording? Somebody can stop the recording.